Hello everybody, welcome back. So in this session I'm going to cover the logical instructions, and the instructions that are highlighted in green are already covered in the previous videos. If you haven't watched, please watch the suggested video above. So this is a group of instructions which you're gonna see in this session. So there are two categories. One is the shift operations and second one is the bitwise operation. So the naming convention for this shift instructions are like this. So first S for shift, and second letter is for the direction, which is left or right, and third letter is for the functionality, which is like logical or arithmetic. Okay. So the shift instructions and operations are very familiar to embedded developers. But if you are a newbie, then it might be a little bit difficult to grasp. But at the same time, I don't want to get into the binary number representation and computer architecture. So what I have tried my best to strike a balance in between. So that's why I have represented this number in bits for easy understanding. Okay. First, the syntax for the shift of logical is SLL and the destination register, operand 1 register and operand 2 register. What this does is, like, the value in the operand 1 is shifted by the positions mentioned in operand 2 register, and the result is stored into the destination register. So let's assume that we have this number in T0 register, and I have expanded that into bit nibbles here. So 000000724, so that's this value. And if we, let's say the T1 register has 15 in it, so once you execute this instruction, so this value should be, or every bit should be shifted to the left by 15 bit positions, and then the moment it crosses the boundary, it is going to be discarded or eliminated. Okay, and the new bits that are introduced on the right are always going to be zero filled. Okay, so if you see here, so this one should be moved to 15 bit position. So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15, so it comes here, and the new value becomes like 0 3 9 2 0 0 0 0, which is this. Okay, but just a note here, bits beyond boundary are lost. They are not wrapped around. That means once you shift, these bits are not wrapped around into the LSB side. Okay. The same shift left logical with immediate value. So the syntax is going to be like this, but the immediate value are bounded by 5 bits. So this can be of maximum of 5 bits wide, which is like 32. That makes sense because each register is 32 bits wide, and the maximum you would like to shift is by 32 positions. That's why the syntax is limits you up to 5 bits. Okay. So here, just for an example to show you, if we shift beyond the like, let's say that we have valid values which get shifted beyond the boundary, then what happens? So we have this one here. If we do a logical left shift by 23 bit positions, so it comes all the way up here, but this is a boundary, so this will get eliminated. You see this, the rest of the bit buttons here comes here, so this value becomes like 920 followed by all zeros. So this is the new value. Once you do shift of logical immediate on this by 23 bit position, you get this. Okay, so now we go let's see the shift right logical. So it's almost the same, except that the bit positions are shifted to the right. Same for right logical, this is the syntax. So shift right logical, destination register, operand 1 and operand 2 registers. Okay, so even in this case, the bits that are shifted beyond the boundary are lost, not wrapped around to the MSB side. Okay, so same value, and 4 in the T1 register, if it's shifted by 4, so these 4 bits will be lost, and all the nibbles are shifted to the right by 1, and 4 bits are introduced here, these are always 0 filled. In logical shift, these MSBs are always 0 filled. So shift right logical immediate. Okay, so same right side, then immediate value, same result. No big difference, but just for a change, I have changed the input value for a reason. I have introduced sign bits here. Once you do the logical shift on the right, so there are sign bits get shifted to the right, but the MSBs are always 0 filled and introduced. Okay, so this is shift right arithmetic. So as you know, the most significant bit is the sign bit. Okay, in the in this representation or in any computer representation. Okay, so when you shift this value to the right by 4 bits, so this gets lost, okay, or get discarded. So this nibble is shifted by 4, this comes here, this comes here, same way. So these 4 zeros come here, and there are 4 zeros introduced in the most significant bit positions, but this is not always 0 filled. This is not, this is, should be the sign extension of this. What does it mean is, if the most significant bit is 1, these are all going to be filled with 1s, and if the most significant bit is 0, these are all going to be filled with zeros. So the syntax is sra, and destination register operand 1 and operand 2 registers. So again, within immediate value, but here I have taken an example. This is a signed value, so let's see how this works and how does it differ from the logical. If you see in the previous case, and what is this? Yeah. If the sign bit is 0, then the shift right arithmetic and shift right logical results are almost the same. Okay, but if the sign bit is 1, then the shift right arithmetic is gonna extend the sign bits into the introduced most significant bits. Okay, almost the syntax is almost the same, and the immediate value is limited by bounded by 5 bits. So there is nothing called as a shift left arithmetic. The reason is very simple, because the arithmetic makes sense only when the sign bit is 100. When you shift left, then the sign bits are not 100. That means that you don't need, it doesn't make sense to have a shift left arithmetic. So bitwise operations. So again, there are 2 variants, like a register instruction, and the next one is immediate with immediate value. So I've taken an example here. So T0 has this value and T1 has this value, and this is the result of AND bitwise operation. This is OR bitwise operation and XOR bitwise operation. So in the bitwise operation, the operations are performed on each and every bit. So for AND, if both the inputs are 1, it's going to be 1. Otherwise, it's going to be 0. So okay, this should be 1. Yeah, you can see a 1 here. Yeah, 1 here. So all zeros. For OR operations, if any one of the input is 1, it's going to be 1. So it's a 1 here. It's a 1 here. It's a 1 here. And that's the OR operation. And for exclusive OR bitwise operation, the input should be exclusive of each other. So one should be 0 and the other one should be 1. If both are same, like 0 0 or 1 1, it is going to be 0. Okay, take a moment here to explain the difference between difference and importance between arithmetic shift and logical shift. So I'm just going to assume that I have a 4 bits wide register and not a 32 bits, because it would be very difficult to write and explain here. So for 4 bits, so the minimum value is 0 0 0 0, and the maximum value is 1111, which translates to 0x0 to 0xf in hexadecimal. For the same range, if you consider that as an unsigned number, then it would range from 0 to 0 to 15. And if you consider them as signed numbers, then it would range from -8 to +7. If you don't know, then 1 followed by 30 is -8, and this is +7 in binary representation as 2's complement. So if you don't know what is the equivalent, if you don't know what is the equivalent negative value for a given number, let's say for +7, take the 2's complement, that would give you -7. So 2's complement is like 1's complement and add 1. So this is the -7. So 2's complement representation of -7. So now why is this important? Why do we have arithmetic and logical shift as here? So let's say that we have an expression -8/2, which should be -4. Okay, so -8, as I said before, this is -8, and if you do an arithmetic right shift, and then so the bits will be shifted by 1 to the right, and it will be sign extended on the MSB. So this is a value, and this is equivalent to -4 into its complement representation. Okay, whereas if you do a logical shift, then this would become like just +4. So it doesn't make any arithmetic sense, like -8/2 is not +4, right? So if you can't lose your sign. But sometimes you might need this, and sometimes you need, whenever there is a arithmetic sense is needed, then you would use arithmetic shift, and sometimes you need logical shift. You don't have to honor the sign. Okay, and this one I think I already explained in why immediate values are always less than 32, because any instruction on a when a platform supports an instruction, that instruction has to be stored in a register. So for example, in RV32I, the instructions are 32 bits wide. So within that 32 bits, there should be an operand, and there should be an encoding for source and destination register, and then it should have this immediate value. So it's always going to be, you cannot fill that instruction with just 32-bit immediate value. That's why. Okay, so I hope that explains and that's helpful. So getting back to the bitwise operations, so there's another variant for passing immediate value. So one of the values in the register, and you can pass the immediate value for bitwise operations are bounded by 12 bits width. So you can pass up to like 0xFFF. Okay, that's the maximum you can pass with. So based on the input, the input is converted into a 32-bit value by sign extension. Okay, so if the most significant bit of the 12-bit input is 0, then this all would be 0, and if the MSB of the immediate value is 1, then this all would be sign extended. Then as before, the same AND, OR, and XOR operations are performed on each and every bit, and the results are stored. And the syntax, this is the one. So destination register, okay, for every operation, so we have AND I, and OR I, and XOR I. Destination register, operand 1, and an immediate value. So I hope that's helpful, and that's the end of the session. And maybe in the next session I would cover branch operation, and then I am planning to do some maybe like a bubble sort or some sorting algorithm using this instructions, whatever we learned till now. Okay, thank you.